In EET, we're not often concerned with individual protons or individual electrons, and instead we're more concerned with the flow of current. And to analyze the flow of current, we're going to kind of make a engineering and physics approximation, and we're going to say that the current flow, if I had a wire, excuse me, I'll put a black pen here. If I had a wire, what's going on when current is flowing in the wire is that there's just a bunch of charges basically stacked up next to each other, and they're all kind of moving in that direction. So the engineering approximation that we're going to make to analyze this situation is called the infinite line charge assumption. And in this situation, we have charges that are all stacked up next to each other, and we will uniformly distribute them along the z-axis. And when we do that, what we want to do is we want to determine the electric field intensity at some point in free space away from this infinite line of charge. So we could imagine that the z-axis is a wire, and it's carrying a certain amount of current, which equates to a uniform distribution of electric charge. And what we want to know is, well, if there's current flowing in that wire, what is the effect of that current in producing an electric field at some point in space? So the first thing that I'd like you to kind of refresh yourself on, though, to solve this is the use of cylindrical coordinates. Using cylindrical coordinates to solve this problem just makes the math much, much easier. And so just a reminder, quick refresher, in cylindrical coordinates, the location of a point in space is given by rho, which is the distance of the point from the positive z-axis measured. This is measured normal to the z-axis, meaning that that little tangent line makes a right angle to the z-axis. Phi, which is the rotation measured from the positive x-axis to a projection of rho onto the xy plane. So that's phi right there. And then, of course, z is just the height of the point above the xy plane. So it's how far up in the z direction it is. And so we have a point that is a function of rho, phi, and z. And we'll be using this coordinate system to solve the infinite line problem. First thing I want to say about this line is that it has uniform charge density, and I mentioned this earlier, and I want to just extrapolate on that. And what that means is that we've got a uniform distribution of coulombs along its length. And so it's not that this line has 10 coulombs of charge, it's got charge distributed along it. It's like the charge is spread out along it. And so we call this linear charge density, rho sub L, and it's given the units of coulombs per meter. It's how many. It's kind of like Henry's per meter, or the distributed parameter model of a T-line, but this is charge that's been distributed along the length of this wire. So don't confuse this rho sub L with the rho that is in the cylindrical coordinate systems, and just do note that the unit, since the charge is spread out along the length of the wire, is coulombs per meter. So let's now consider the point at space at which we want to determine the electric field strength. In the cylindrical coordinate system, again, this point is given as a function of rho, phi, and z. And phi is the displacement as measured in rotation from the positive x-axis, and z is the displacement in the positive z-axis. And the reason we want to look at the point in cylindrical coordinates is that it's going to help us to determine some intuition about which way the electric field is pointing. And to do this, what I want to do is first consider the phi rotation around the z-axis here. It's fairly obvious, I think, that no matter what angle I choose for phi, if the point is located here in the phi, 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 the magnitude of the electric field strength measured at that point where rho is constant but phi changes, it's got to be the same value. By this I mean the electric field intensity has to be independent in rotation in the phi dimension, right? If I measure if this z-axis contains the uniformly distributed charge density, if I measure here, the field strength has to be the same as if I measured here, 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 here. Clearly, it's going to be pointing a different direction. It's going to be pointing in that direction here, and pointing in that direction here, pointing in that direction here. But the magnitude of that electric field strength is going to be the same, so it's independent of rotation around z. So if I fix rho, which is this length, and I fix z, which is the height here, I'm going to get the same value of E no matter what value of phi that I choose. And what's useful about this observation is that it's going to allow us to analyze the problem only in the z and the rho plane. So what we'll end up doing is we will plot the effects of this uniform charge distribution in the infinite line charge along the z-axis, this axis here, and then along the rho axis here. So now we have a point in space, and it's just going to have two dimensions, a z dimension and a rho, that should be a little curvier, a rho dimension. And we want to look at which direction the E field is going to point. So, and to analyze the situation, what we're going to consider is that the line is infinitely long, which means no matter where I choose my point along the z-axis, there's always going to be as much charge below it as there is above the point, above it. So say the z-axis has this infinite length of line charge, and the special property of it being infinite is even if I pick a point here, there's as much charge above it here as there is below it there, because there's infinite charge that direction and infinite charge that direction. That is to say, the total charge above this point is going to be equal to the total charge below the point, and therefore there's going to be what we call charge symmetry along the z-axis, right? The effect, say I want to measure the effect of this at this point right here. Well, if I measure the effect of that, remember that should be a straight line. It's not the best straight line, but the effect of that there is going to be a straight line there. Well, remember there's always going to be a charge canceling it right here. And for every charge up here, there's going to be an equal charge down there. So the upwards component of this charge is always going to be canceled by a downwards component here. And what the net result is that only these two will add together. And the effect is that the electric field won't point in the positive z-axis. It won't point in the negative z-axis. It's only going to point in the rho direction. So in the case of the infinite line charge, we kind of develop an intuition that the results have to point only in the rho direction. And so that's a little bit of, again, a qualitative understanding of what's going on in the infinite line charge case.